Dear students, after studying this module, you shall be able to know the synthesis and the reactions of medium and large ring compounds. The cyclic compounds have played an important role in the chemistry for a long time. The interest towards the macrocycles and macroheterocycles has increased due to the wide applications. The development is mainly due to their fascinating structural symmetries and new stereochemical aspects. Also, these compounds build a new class of host systems and can be used as concave building blocks in supramolecular chemistry. The cycloalkanes, also called as cycloparaffins, are conceptually among the simplest classes of organic compounds as they are composed of only carbon and hydrogen and only one type of structural component. The cyclic species with 8 to 12 ring members are called as medium rings, and with more than 12 ring atoms are defined as larger rings. The term macrocycle refers to medium and large ring compounds. The cyclooctane is the first compound of this series. The three basic conformations of cyclooctane are boat or BB conformation. It has diamond lattice but suffers from bad hydrogen-hydrogen interactions. Boat chair or BC. This is the best conformation as it has the minimal inter-electronic repulsions or any kind of interactions. Chair or CC. Since this conformation also shapes like a crown, so this conformation is also known as crown conformation. It has bad torsional angles and hence leads to a strain in the ring system. All the three are shown here in the given figure, where the simplified figure also represents the various interactions in the given conformations. Similar to cyclooctane, a cyclodecane ring also exists in several conformations with two lower energy conformations. The energetically minimized conformation is the boat-chair-boat conformation, which is also called as BCB conformation, while the chair-chair-chair or CCC conformation has significant eclipsing interactions. The X-ray crystallographic studies of cyclodecane revealed that the most stable conformation has carbon-carbon bond angle of 117 degrees. This indicated some angle strain from the normal of 109 degree 28 minutes. So this bond angle allows the molecule to expand and minimize unfavorable repulsions between the hydrogens across the ring. Synthesis of medium and large ring compounds. Intramolecular condensation of alpha-gamma aliphatic dicyanides. Alpha-gamma aliphatic dicyanides in presence of an alkali form cyclic ketones, which can be further reduced to cyclic alkanes via Clemmensen reduction using zinc mercury and HCl. Here it can be seen that how dicyano compound can be converted into a cyclooctane ring system. In the presence of the lithium compound, the hydrogen is lost from the alpha position of the cyano compound, leading to further decyclization by the intramolecular cyclization method in the presence of an acid. The carboxylic compound obtained is then heated to lead to decarboxylation and the formation of an ketone compound, which in presence of zinc mercury amalgam and HCl undergoes the Clemmensen reduction, leading to the formation of a cyclic structure. Synthesis using Dieckmann condensation. A diester compound undergoes an intramolecular Claisen condensation in the presence of a base like an alkoxide ion, forming cyclic ketone, which can be reduced to cyclic alkane via Clemmensen reduction using zinc mercury amalgam and HCl. This reaction primarily takes place in 4 steps. Step 1 is the abstraction of a proton. A strong base like an alkoxide ion abstracts the alpha hydrogen from one of the ester group and forms an enolate ion and an alcohol. The alcohol and an enolate ion is formed by the tautomerization. Enolate ion attacks an electrophilic carbonyl carbon of another ester molecule and forms a beta keto ester product along with the regeneration of the base. Hydrolysis and decarboxylation is the step 3, wherein the product beta keto ester is hydrolyzed and further decarboxylated on heating to form a cyclic ketone. The last step involves the Clemmensen reduction, where the cyclic ketone is reduced to a cyclic alkane via Clemmensen reduction using zinc mercury and HCl. The whole process involves a intramolecular cyclization of the 2 diesters. One of the ester, as can be seen, has led to the loss of a proton, forming an anion intramolecularly, reacts with the other carbonyl, leading to the cyclization and the formation of a ring structure. Further elimination and the reduction leads to the formation of a macrocyclic diester compound, and in turn which is further reduced to the formation of the cyclic alkane ring system. Synthesis of cyclooctane from buta-1,3-diene. The cyclooctane and the derivatives can be synthesized from butadiene involving dimerization reaction. The reaction is catalyzed by metal complexes like nickel, bis, cyclooctadiene. The dimerization leads to 1,5-cyclooctadiene, which is in then turn reduced to cyclooctane by help of the hydrogen using palladium and charcoal as a catalyst. The cyclooctane is also synthesized by the catalytic reduction of cyclooctane, cyclooctadiene and cyclotetraene using palladium charcoal and hydrogen as a catalyst, as represented in the given scheme. It is a simple hydrogenation reaction leading to the complete reduction of the unsaturated systems. Synthesis of a substituted cyclodecane. The oxidation reaction of octalin with ruthenium oxide and sodium periodate in mixture of solvents like carbon tetrachloride, acetonitrile and water gave cyclodecane 1,6-dione in more than 75% yield. As it is represented in scheme 5, the reaction leads to the formation of a dione system, a macrocyclic 1,6-dione system. Synthesis of cyclodecane from buta-1,3-diene. The cyclotrimerization of buta-1,3-diene gives cyclododecane 1,5,9-triene. The reaction is catalyzed by a mixture of titanium tetrachloride and organoaluminium co-catalyst. The cyclododecane 159-triene is further reduced with hydrogen in the presence of nickel to form the required macrocyclic compound. It has been very nicely represented in the scheme. Reactions of medium and large ring compounds. The chemical reactions of medium and large ring compounds follow our usual cycloalkane reactions. There are two major types of reactions of alkanes and cycloalkanes. Combustion. Cycloalkanes and alkanes react with oxygen, forming carbon dioxide, water and heat energy. Halogenation. They tend to undergo the reaction with the halogens, forming alkyl halide and hydrogen halide along with it. However, some of the typical reactions are discussed here. Isomerization of cycloalkanes. The cycloalkanes with more than 6 carbon atoms undergo skeletal isomerization over SO4 zirconium oxide in liquid phase at about 50 degrees centigrade. The reaction of cyclooctane under similar conditions give ethyl cyclohexane as a major product. Functionalization of cyclooctane. The cyclooctane performs the reactions of saturated hydrocarbons like combustion and free radical halogenation. In a typical work, a cyclooctane reaction with nitrobenzene using peroxides such as dicumyl peroxide to get introduced a phenyl amino group in itself. It is shown here how a nitrobenzene reacts with cyclooctane ring in the sealed tube at the temperature of 130 degrees, and the reaction carried out for 16 hours gives the required product. Aldol condensation with cyclodecane 1,6-dione. Cyclodecane 1,6-dione reacts with a base like sodium carbonate to undergo aldol condensation to form an alpha-beta unsaturated ketone in 88% yield. The reaction provides the formation of 5,7 fused hydrocarbon skeleton. This is a base-mediated aldol condensation of cyclodecane 1,6-dione. Photonitrosation of cyclododecane. The reaction of cycloalkane using nitrosyl chloride NOCl gives photonitrosation product. This reaction is generally carried out in an organic solvent, sulfuric acid, in a two-phase medium using mercury lamps or sodium lamps. An oxime is thus produced in the organic phase and is subsequently extracted in the form of oxime hydrochloride by the sulfuric acid phase. The reaction of cyclododecane under this reaction condition yielded cyclododecane oxime hydrochloride. Ring opening reaction. The oxidation of cyclododecane opens the ring to give dodecane dioic acid. The reaction is facilitated by nitrogen oxides. This reaction does not encounter the danger of too violent a reaction, even at high concentrations of nitrogen oxides. Also, this reaction proceeds with good reaction rates. The higher dicarboxylic acids are of special interest in the field of polyamidic resins, plasticizers and lubricants. Dehydrogenation reactions of these macrocyclic ring systems. The reaction of cyclooctane with iridium catalyst in the presence of hydrogen acceptor gives cyclooctane. The reaction is carried out in the presence of indium catalyst. Oxidation of cycloalkanes. The oxidation of cycloalkanes usually gives cycloalkanones and cycloalkanols. Hydrogen peroxide as oxidant is more preferred reagent over the oxidation in appropriate solvent and or metallic organic frameworks. The oxidation of cyclooctane was carried out in acetonitrile solvent using hydrogen peroxide as an oxidant to give the cyclooctanone as major product. To summarize, the cycloalkanes, also known as cycloparaffins, are conceptually among the simplest classes of organic compounds, consists of only one carbon and hydrogen and only one type of structural component. The cyclic species with 8 to 12 ring members are called as medium rings, and the ones with more than 12 ring atoms are defined as larger rings. The cycloalkane ring compounds exist in boat and chair conformations as individual conformer or in mixed conformers as boat-boat or boat-chair or chair-chair conformer, etc. The cyclic medium and large ring compounds can be synthesized by various methods similar to small ring compounds. Some of the typical methods are intramolecular condensation of alpha-omega aliphatic dicyanides, synthesis using Dieckmann condensation, synthesis of cyclooctane from buta-1,3-diene, synthesis of substituted cyclodecane, synthesis of cyclododecane from buta-1,3-diene. The chemical reactions of medium and large ring compounds follow the usual cycloalkane reactions. The two major types of reactions of alkanes and cycloalkanes are combustion and halogenation. Some of the typical reactions discussed have been isomerization of cycloalkanes, functionalization of cyclooctane, aldol condensation with cyclodecane 1,6-dione, photonitrosation of cyclododecane, ring opening reaction, dehydrogenation reactions, and oxidation of cycloalkanes.